What's the conversation today, Zach?
Well, Max, this week we're going to dive into some new code, which is, I think,
Yeah.
fascinating. It's chapter 32 of ASCE 722, which is tornado loads.
Heck yeah. It is very surprising that new code is coming up. It's not that we just invented tornadoes. 716, I remember, felt like a very modern code when this came out. There are other changes, right? We have more data, but I'm jumping into details here. But we have this whole new chapter on tornadoes, and it is curious to me that it kind of just came out. And we're going to dive in and see what we can learn from this and see if we can share any info.
I think just starting off, the most important thing, I just want to throw it right here at the beginning because I feel like
Go for it.
if you can't make it to the end, that's okay. But is that chapter 32 is drastically different than what we do with ICC 500 storm shelters. Totally two different things completely. They're both tornadoes.
Yeah.
But the uses are totally different. So I just want to throw that out right now, as if you're thinking that this is tornado shelters, it is not. So keep listening so you can learn more about chapter 32.
Yes, that is an important takeaway. These are different items.
All right, Max. So let's talk about why tornado loads and why now. Why did we wait till ASCE 722 for it to come out? So
Gosh, yeah, I know.
what drove
Well,
ASCE 7 to introduce a full chapter on tornado loads?
from what I've heard, the Joplin, Missouri tornado in May 2011 was really the kickoff that led the committee here to think about the damage that is done and can we help. So this tornado was an EF5. So we're talking 200-mile-an-hour wind speeds. It killed 158 people, caused about $3 billion of damage, uh, 4,300 homes destroyed, 553 businesses. So it did some pretty serious monetary damage. And of course, insurance, the cost here could drive a lot of decisions. So I think that was a really big thing, talking about like how can we not have this much damage from one string of tornadoes. So that was really the kickoff that had people discussing about this. SK Gosh has a few talks on this and talked about how this originated, but that is sort of the takeaway, right? This Joplin, Missouri giant tornado, and it was a pretty big issue.
The first thing that comes to mind is the word resilience. How resilient can we make a community from, especially an economic standpoint? You said $3 billion with a B. It's a big cost. And, today we're not talking about all buildings. This doesn't necessarily apply to this chapter, but, how do we design for more loads that are important to some of these structures? So Max, why were tornado loads historically excluded from standard design practice?
So 716, we started to see this pop up. And honestly, when I was thinking about this was very similar to the elevation factor, right? It was, we knew it existed, so enough to put it in the commentary, and then it came into code right after the 710, 716. So this is one sequence beyond, but we had 8 pretty darn dense pages in the commentary. So we had some principles for a serious hit. We had the storm shelters were defined in IC 500. I actually comment on that as I saw in a presentation that there has never been an IC 500 failure, and the presenter was really pushing that, like, look how good of a job we did here. I kind of see that as I feel like we might have gone too far if there's never ever been a failure, but that's for a different presentation. Anyway, historically, traditionally have been thought of as very low frequency, and it's only going to hit 1 or 2 buildings. This is honestly what I was thinking about is the old movies that you have is the tornado shelter, you go hide in the basement and then it hits one farm as it goes down. And it's a real bummer for that person, but everybody else, they have a story. So that is sort of my takeaway. You have anything to throw on there?
I found you sharing that, which is interesting. I mean, 0 failures of storm shelters. I think such an interesting concept because we learn in engineering from our failures, right? All the history of the loading that we have today and the way we design things is from majority of the time, not always, is from previous failures. So I find that as an interesting fact that you learned. It's probably a good thing. I've thought in my career before when, evaluating or designing storm shelters, the few that I've done, of just like the loads that this shelter would see, and it's really hard to get your head fully wrapped around. If it's especially it's inside the building, so the building's sitting on top of it, something
The
flying
building can
into it.
fall on it. Yeah. They
So
are
like
robust.
thinking,
I've only done one, but they're
yeah,
pretty
and so maybe
wild.
the building's arching almost over at some action because it fall. So it's like interesting to me. I would never have guessed zero. So it's really the thing
Yeah.
on top of mind, and maybe it's more like commercial buildings that haven't failed. But
Yeah.
I imagine if someone built one in their basement and said, "This is my storm shelter," right, which would not be an ICC 500 certified shelter.
I got a good one in my basement.
So Max, how does ASCE 7 define tornado hazard levels and recurrence intervals?
Okay. Well, very similar to a lot of the other loads that we look at. So, risk category 3 buildings for tornadoes, we're looking at 1700. And for risk category 4, we're looking at a 3,000-year return period. These are pretty big numbers if you're just looking at them alone. To give you a full reference here, so for earthquakes, we're looking at 2,500 MRI. Those have importance factors. That's a little bit different. Wind risk category is 700 for category 2 buildings, but very similar. 1,700 for category 3 and 3,000 for category 4. Snow is a pretty weird one. That's like loosely a 50-year MRI, but that one is thought about differently. So yeah, it is in the pool of everything else. It fits very nicely to the mean recurrence intervals that we sort of expect.
I can see that making a lot of sense. How do tornado wind speeds differ from hurricane and wind speeds in terms of intensity, duration? It's,
Uh,
it's footprint.
yeah, they are different as far as I understand. I haven't done that much hurricane analysis. I mean, I've always lived in the middle-ish of the United States, so the little Maine. Anyway, the impact testing is the same. I can tell you that one. So in this case, we would maybe have windows that an 8-foot 2x4 has to hit at 35 miles an hour. The wind speeds in a tornado are generally less. Hurricanes are pretty robust, but they are quite different. So it's really hard to just compare them side to side. It's almost I was going to say a storm shelter. They are very different, and so they do not overlap that much. Zach, so can you kind of kick us off because you've done some of this design here? Where would we start in a design? I've watched some presentations on this, but I don't know.
Yeah. So the nice thing is they gave us something engineers love, a flow chart. So figure
Ooh.
32.1-2 is the process of determining when design for tornado loads is required. And it is really straightforward. And I really like this. There's 4 things to check. And anytime one of these things is no, you just move on and it's not required. So the first thing to talk about is risk category. This is chapters only required for risk category 3 or 4, per ASCE 7 chapter 1.5, where it's defined there. And if it's no, you move forward. If it's yes, we move on. The next section is it in a tornado prone region? Now there's this map in ASCE 7, 22, figure 32.1-1, tornado prone regions. It is more or less east of the Rockies and 2/3 of the country, majority of the country is what
Yeah.
would be defined as tornado prone. It's not exactly the Rockies, but relative location within the country.
And we're talking Florida to Maine. It's the
Whole eastern seaboard.
I'm surprised by this. I
Yeah,
think I'm
funny
used to
enough,
the
I looked this
ICD
up.
500 map, so
Yeah, since you lived in Maine for a while, I was like, how many times does Maine get tornadoes? And it said on average twice a year. There's
yeah.
some
Do you
level
know
of tornado.
there, there's been a tornado in every state,
The lower 48 or all 50?
all 50.
What a
Yeah,
fact,
like
Max.
that. I don't know. That kind of surprising.
Okay. Okay.
Yeah.
Interesting. Okay, and then the next part here, so tornado prone region, yes or no? If it's yes, we move on. And then so in ASCE 722, you'll see in chapter 1 and chapter 2 there's a new figure, V sub T. It's a new thing that's introduced, and you'll see it a lot. So in our load combinations, you'll see wind or wind sub T or W sub T. And that's just saying like whichever one, governs. And so right here, we go to our new charts and that are in the code. So that's 32.5.2. And you figure out, is my tornado loading greater than 60 miles an hour? And to me, that just blew my mind. Like
Yeah.
we
I was also
designed
very
for so
surprised
much
by
higher.
this. Yeah.
And so everything is just factored and looked at a little bit differently. So I found that very intriguing. And the maps, in my mind, tornadoes 200 plus mile an hour, like the maps would be just super high, but they're not. It's very interesting to look at. So if it's greater than 60 miles an hour, we move on.
I know we're going to circle back around to this, but what controls the tornado speed? Big picture.
Okay, so big picture. So Tornado Alley.
The
I love you
area of the
asking a question
building.
that you know and I don't know. So Max, how are the maps laid out now in the new chapter 32?
Okay, so I had looked in this a little bit because this number surprised me. The VT has to be greater than 60 miles an hour. We have lived in high wind areas. Everything is 60. Like that's such an insignificant number. This is a lot different, and it's tied to the probability of a direct hit from the building. So the larger the footprint of the building, and this is the plan area. So if it's a hospital and it's got its little mains building on the side that's required, tie those things together. So it's anything in a plan area that can be hit. And then also the risk category is tied in here. So, it was hospital or police station, but this is what gets our tornado speed VT up in the, low hundreds, maybe in some cases. So we're going to talk about more of these details, and we don't exactly have the numbers memorized, but this VT of 60, that is a small number. That really threw me.
Absolutely. And please be patient with Max and I. We've dove into this. We haven't implemented it on any projects yet. So we're just trying to get the information out to you guys as quickly as possible. That leads right into the next piece. So one thing that's interesting with these figures is, as you said, the area. So there's two ways to look at it. You can do this the smallest, which would be the polygon method. So kind of drawing lines from point to point around your building, which would provide you the total kind of area, but it's not the area of the building. It includes the space between the points. Please look at the figures in chapter 32 to really make sense of this. To simplify it, you can make it a big rectangle.
I just want to throw, because there's a great term here, the smallest convex polygon that you can shoot. So that is the name of the shape. It's a small convex polygon. But anyway, continue.
Yeah, so as Max said, the small convex polygon method gives you the smallest shape, which will then provide you lesser load. But there's also the simplified rectangle method. So just make a big rectangle that encapsulates everything. You please go look at these pictures.
Why would you not just do the rectangle?
Because it may increase your load, especially because it's not just the single building. So if you have a campus, this is a new piece of the code that is not really referenced anywhere else, is this campus thought. So if you have a campus, the example that's used is a hospital with a central utility plant is one of the examples. You actually have to look at the whole area of that kind of site that encapsulates all those pieces. It's going to be hard to fully understand what that means listening to this, but again, go take a look at those charts. And then let's say you have a campus that has a couple of buildings that are non-essential facilities. Those don't count within the square footage kind of area. So it's an interesting approach to look at things. But I think the hospital idea is great. You have the main hospital and central utility plant. They're both category 4 because of how they're used. So bigger area. So more area, more load.
More likely to be hit.
Yeah. So our last piece of this flow chart is based off exposure. So B, C, and D. And then you look at your tornado wind speed versus your regular wind speed. And so there's factors associated with each one of those. And if your tornado wind speed is greater than the factored normal wind speed, then you continue. And that's the last piece. It then tells you to get into tornado design loads and that they're required for your building.
Sounds fun. It is a nice, clean order of operations.
Yeah, I think logical and pretty straightforward to work through. And truly, I think most of this chapter is really straightforward. It's just a little bit different than how we've done things before. If you need to consider tornado loading, kind of just work through the wind design for main wind force and CNC and kind of see which one governs your regular wind speeds or your tornado loads. So what I thought would be really good to give some context and some actual numbers to this is go through a design example together here, Max.
Heck yeah. Do you have something sort of planned out, buildings and by location and some size? Do you have any sort of framework for how we should think about this.
Oh, that's really funny, Max. I fully do.
I had a hunch.
Okay. So I laid out a couple buildings and a couple square footages just to get us, some numbers. These are rough numbers, so please, for your own project, don't reference what I'm talking about. But, go run the loads and everything yourself. So for this example, we're going to look at a risk category 4 building or facility. We're going to have two cases, a 10,000 square foot building and a 1,000,000 square foot essential facility that has a 10,000 square foot single building on its site. And then we're going to look at two locations, one in Colorado and one in Kansas. The Colorado wind speed will be 135 mile an hour just for our traditional wind. And then for Kansas, it'll be 122 mile an hour ultimate wind speeds. We're going to look at wind exposure C, and then we're going to make an assumption that it's an enclosed building for both wind loads and tornado loads. So we can use that as kind of the groundwork for working through this. So if we go through our flow chart, we pass the first piece. It's a risk category 4 building. So we continue. Are they in a tornado prone region? If you look at the map, they both sit in the kind of gray area that says tornado prone. Also, if you go to your ASCE hazards tool online, it will tell you if your building's within a tornado prone region or not. So as you get along that line, it's going to be really hard to dictate where it lives. So that can help you.
I want to say, because I'm looking at this map here, that our Colorado Front Range location is right on the edge, right? So this might have lower loads. And then Kansas location is basically in the center. This is what IC 500 this is Tornado Alley. So these are going to have much higher tornado loads, but we know that the wind loads, Colorado is, in this case, 10% higher base load. So we'll keep that number as a balance in our head.
So then we move on to the next piece here is our V sub T greater than 60 miles an hour. And we find that that is true, again, by running our hazards tool online. So for our Colorado location, we will, for our first building that's 10,000 square feet, we're actually at 50 miles an hour. So we are less than our load. So it actually is not required. When we're at the 1,000,000, we're at 81 miles an hour. So we're greater than 60 miles an hour. So we say yes, and we continue on. This is similar for the Kansas location. For both the 10,000 and the 1,000,000 square feet, we're above 60 miles an hour at 99 and 125 respectively. So then we go to the last section here, exposure kind of categories. So we're C. So if we're in the Colorado one, we don't need to design for it. For the first building, the 10,000 square foot, as we already saw, we got out of that at the step before this. Now at the 1,000,000 square feet, funny enough, for exposure C, it's 0.6 times our design wind speed. So 0.6 times 135 is 81 miles an hour. And our tornado speed is 81 miles an hour. So we're equal there. So we would design for tornado loads and move forward there. In Kansas, for our 10,000 square foot building, that drives us to designing for tornado loads, 74 miles an hour versus 99. And then for the 1,000,000 square feet, we're 74 versus 125. So for the 1,000,000 square feet in Colorado, and then the 10,000 and 1,000,000 square feet in Kansas, we would be moving forward from here. But for the 10,000 square feet, we wouldn't need to proceed any further. We would stop and we would just go to designing for our typical wind speeds.
All right, Zach. So I know we have tornado enclosure classifications. I don't know anything about this, but this is in 722, chapter 3212. Can you tell me anything here?
Yeah. So if a glazed opening is required to be functional for the facility, then the opening must meet another section, and I'll get to that in a second. And if it's not required to meet it, then you have to consider it as an opening in your building, as we look at for internal pressures there. Thank you, Max. So if it is needed for the functionality of the facility during a tornado, then we go into a section of required glazing, and that is impact resistance. So it's a missile level of D or E, which, as you kind of mentioned earlier, it's about an 8-foot long 2x4 at 35 miles an hour is D, and the same 2x4 at 55 miles an hour is an E. So to me, this is a very interesting piece of the code that kind of pushes us back to having discussions with the architect of making sure that they're meeting this ASTM standard of kind of missile loading for the openings or for the glazing.
I like this data. This is I'm sure this is stuck in the code for a very long time of let's just shoot a 2x4 at it and see what happens. It just feels old fashioned, but still works.
I just really want to be part of the testing is what
Yeah.
I've thought about a lot here. So to summarize a little bit about the buildings we talked about, for that building that's 10,000 square feet in Colorado that isn't required, um, Max, how much do you think the wind speed or the pressure, excuse me, differs from the regular main wind force to the tornado main wind force?
Um, I bet in Colorado, I've never been hit by a tornado in Colorado, so I think the load is going to be quite a bit smaller. I'm going to say 75%. So maybe our main wind force is 25 or 30. So we're, I don't know, 18 to 22.
Yeah, yeah, it's great.
Oh, really?
So we're getting close. I mean, it is significantly less. So if for this building we're about 40 miles an hour or 40 PSF, for our regular main wind force, tornado would take us down to 6. So nothing nothing there to really focus on other than just to say that, it doesn't really govern. And it really proves by running the numbers. The million square feet in Colorado, it goes from 40 PSF, as we kind of already said, down to 15. So again, doesn't really govern for our main wind force. And when we look at our CNC loads, again, kind of similar thing. I was pretty surprised that there's such a big difference in how much lower it was.
Okay, so that's not that bad. What if we had the same building in Kansas, which I've heard has a few tornadoes?
Yeah, sure does. So from a main wind force standpoint, we're still going to be governed by our regular winds and not tornado loading. But when we dive into the components and cladding, that's where everything changes. So not
Hmm.
everything is governed by tornado CNC, but majority of things. Still a couple of the regular CNCs. So this is where it starts becoming interesting of having to really run both and understand where it differs. And then when we get to our last thing here is our million square foot in Kansas. Tornado for the main wind force governs, but it governs by 35 PSF versus 32 PSF. So a slight increase there. Again, what I'm trying to think through as an engineer is how much is this going to affect my designs? And 3 PSF on the main wind force, especially for a large facility, could increase things substantially, but we're not doubling the load.
Yeah, I was gonna say 3 PSF is like it's not that much in the scale and the percentage sense, but
And then this is where the biggest changes that I found or the most increase is the CNC. So it almost doubles. I think in almost every category for this million square feet. Again, this is the complex is a million square feet and the building's 10,000. So um, everything is almost kind of sort of doubles. So what that makes me think of is our cladding. Like what cladding attachments uh, can see these higher loads, which could drive different architectural finishes. So Max, summarize from all of that data, what were your big takeaways?
Colorado should be pretty safe as long as you're close enough to the mountains is my biggest takeaway. So I'm going to be over here, but that the loads are not that serious and they are more specific than I originally thought. Right. So when I was looking into this, it just had jumped in my head that all buildings need to be tornado designed now to some low tornado pressure, but this is not the case at all, right? This risk category 3, 4 cutoff, that is a very small percentage of buildings. And this is also like a high importance factor in seismic. Like we have way different loads going into these very important buildings, which would be for protection in case there is some serious issue. So we need these to be in place. And then also, it was not in my experience doing an IC 500 storm shelter. That was a robust building, right? These are concrete masonry walls, like it might be a wood wall, but it's full of sand. It is it is not asking that we do that level of strength or resistance to a flying 2x4. It is still a reasonable load. So it's in general a lot less than I thought it was going to be.
I was really
Mhm.
interested when reviewing everything that there wasn't just a factor, like you had mentioned with seismic, that we have
Yeah.
just an increase factor. But then when you look at all the numbers and how things are developed for CNC and main wind force, kind of makes sense. It's not just a direct factor increase, but um, yeah, I found it intriguing and kind of exciting to see that the loads wouldn't be mega. I don't know. I was thinking for some reason that the main or like the CNC loads for for the normal wind would be 40 PSF, and all of a sudden now for chapter 32 they'd be 300 PSF.
Yeah. Yeah.
And maybe went from 40 to 60 or 40 to 80 for CNC, but which is substantial, but not as much as I initially thought it would go to. So
Okay. In that context, then, what are the biggest challenges that you see in applying 32 to real projects, right? Let's just take this from presentation to you're doing a project next week. What's the issue you see?
a couple things. One, I think the education of the owner and the architect, our likely client on this, is just describing and helping them understand what this new type of loading may be, because it doesn't just affect what we're designing on the building structurally, as we talked about the missile impacts. Those are things we need to communicate to architects that may not be used to designing for that. Here in Colorado, probably not as
Eh,
likely. But now this section of the code tells them they need to, or we need to consider it an opening or glazing that's not needed during an event. So maybe it changes things. It'd be interesting to see how that all gets implemented. And to me, that's one of the bigger things is the doors and windows, and just how we as structural engineers communicate that to architects, and also how do we explain to them and owners that they need to get these impact resistant doors and windows. So, Max, how should engineers approach tornado design for shelters versus typical buildings?
Yeah, so we said this on the kickoff, but just to kind of repeat that these are dramatically different than the IC 500. These they don't interact basically. Storm shelters and typical buildings. So, where we might see the IC 500 buildings, just to give you a scope, this is Tornado Alley, sort of central US. This is go like hit the west side of Pennsylvania all the way to, I don't know, mid Kansas. And then it does hit North Texas to Michigan. But this tornado area is a heck of a lot larger. And we're only going to see we're gonna see effect in high risk category structures, but it's also gonna be heavily component cladding loading, not the main wind force, or especially in seismic zones, which I guess this is not. But yeah,
Yeah, I find one thing that's interesting, and the best way to separate these two is ICC 500 storm shelter is exactly that. It's a shelter typically within a building. ASCE 722, Chapter 32, tornado loads is the building. So it's the main wind force and CNC, where ICC 500 shelters or something that you'd find inside of a building that you'd shelter for a more direct hit, probably, of a tornado.
yeah, and this is the chapter 32 is resilience, right? It is not this direct hit of 250 miles an hour. It is a more robust building that is tuned for areas where tornadoes do occur and will cover some insurance costs. Like the building will be in better condition after this.
So, Max, what's the single biggest misconception engineers have about tornado loads?
I think this was the thing that I assumed in the beginning. Also, I guess other people might think this is that with this code change, this is going to be, every building in Kansas is now designed to 200 miles an hour wind. It is not that severe and it is well thought out. So I think that is my biggest takeaway is that these are reasonable loads. This is not changing the way we design every building. This is fitting into our standard design protocol. So the last piece that I had found in some insurance documentation is talking about the claims oh, from a tornado is annually 5 times more than an earthquake and is a little bit more, like a couple percent higher than a hurricane. So this is a pretty serious cost implication. And so that hit right with so that made a lot of sense of how we can do building design better is to not cost everybody more money. So that was my sort of closing. What do you think listeners should take away about the role of 32 in modern structural resilience? What do we got?
Yeah, I think this chapter is really there to speak to a natural disaster that is commonplace, just like hurricanes and wind events, normal wind events, and as well as seismic. I think it's a chapter that was needed to be added to ASCE 7 or to something to be able to give engineers the minimum design values. I think a big thing here is resilience. I think that is what it is driving is for our category 3 and 4, more essential facilities to have some resiliency against these tornadoes, to be more useful and be able to really operate out of these facilities during these events. Hospitals, 911 call centers, fire stations, police stations, really essential facilities during an event like this. Like you said, Joplin, $3 billion in damage, over 150 people died in that. I mean, that's a severe event that really that infrastructure needs to work and is really important. So I think finding through these examples, something that opened my eyes was that it's not drastic changes, but significant enough that will change a little bit of how we design that should make our buildings in these areas better.
All right. Well, let's go design some buildings.
Sounds good. Let's do it.